So, welcome everyone. This is our, I guess, first ever time delay system webinar. So, today our speaker is going to be Professor Gabor Stepan from the Technical University of Budapest. And so Gabor spent most of his career at Budapest at the Technical University, as well as at the Hungarian Academy of Sciences. But he also spent about 2 years at University of Newcastle in the UK and 1 year at Caltech as a visiting professor. He is a recipient of numerous awards, but just to mention a few, he received the ASME Thomas Kogi Award, and he also is an ERC Advanced Grant holder. He has served as editor on many different journals over the years, and also contributed to organization of conferences through many organizations, including SIAM, IUTAM, SERP. And without any further ado, I would like to give him the floor. Just one little thing before we do that, I would kindly ask everyone to mute your microphone. There are a lot of people here, and we want to make sure that the talk can go smoothly. So please do that. And Gabor, if you could share your slides, the floor is yours.
Okay, thank you very much. I hope you can see and also you can hear me, hopefully.
Yes.
Just check whether the share sound is okay, because sound will be important. And now we will go to the presentation mode. So thank you very much for the introduction. This is the title page, parameter sensitivity in delay systems. And I mentioned it's also a credit for co-authors, or there are many referring with these dots, but I would still like to mention especially Thomas Hinsberger and Li Zhang, and also Thomas Molnar, a grant student, a student of Thomas Hinsberger. But there are many others who took part in different projects and different results, partly within the ERC project on machine-to vibrations that I will mention, and many contributors are there to the results. And also regarding the balancing projects, the Hungarian-Chinese bilateral fund I wanted to mention. So here is the contents list, which is quite extensive, but we will accelerate. So first I will try to explain the basics in the stabilization problems with time delay a bit in more details, and then as we approach towards more and more applications or even industrial applications, then we will go somewhat faster. So the first topic will be the stabilization, and considering its very simplest example, when you have to consider a block at the top of a mountain or something in a frictionless position, and we of course in this case the x equals to 0 position in the gravitational space, the x equals to 0 position will be unstable. In the phase plane of the displacement and velocity, we have a saddle point with the trajectories, and now we try to balance it with this control force Q. We check the position and the velocity of the block, and we try to feed it back with a PD controller. Okay, so the PD controller will try to make this saddle point into a focus or spiral or node as you want, but definitely would like to stabilize it. So that's what I mean when I speak about stabilization, and often we call it balancing, because if you balance a stick or yourself, that's also the case. So it looks relatively simple. So the question is really, what's the problem here, and why it is so that if you check during the years, if in Google Scholar you type in controlling inverted pendulum, then you will get these numbers in every 5 years. And at the moment, it shows 17,800 publications or contributions in the history, which means that every day about 4 or 5 papers or something appears on the internet, which is related to just to these keywords. Actually, by myself, I started working with this in the 1980s when I had to give a lecture at the academy, and I was asked to give a demonstration. And since it would have been very difficult to demonstrate anything with machine tool vibrations, which is a very tiny motion, and you can only hear something. At that time, there was no video, anything. Then I thought that this might be an interesting example. So that's where my first publications go back. And so that's check what the human PD control, how it works, and how we can establish what I presented in the introduction. Of course, there are several different mechanical models that you can think of. These are all simplified, simple models, the stick balancing or balancing yourself with your arms moving up and down, or in the sagittal plane, balancing yourself with the torque at the ankle or your torso, or even the Segway, or it's not the Segway, it's a monocycle when you try to ride a single-wheeled bicycle, okay, so monocycle. But the equations of motion, if you get it, they boil down to the same thing in the end. So the control torque, for example, in case of this ankle, it's a PD controller based on the angle and the angular velocity. Or if you consider this one, which is already a 2 degree of freedom model, here you also have this control torque. It's an internal torque between your arms and your body. Or if you consider this Segway or monocycle case, then there is also an internal torque between the wheel and the pendulum, which should be used. So the differential equations look different, but in the end, they all can be obtained practically in the same form. So let's see this example. For example, it's already 2 degree of freedom, this planar inverted pendulum, and we try to stabilize it with this force Q. The 2 coordinates are the angle and the position of the lowest point X, and this is the equation of motion. Here is the control force Q with the PD controller, and we can see that the coordinate X doesn't show up only here with this acceleration. Even the control force doesn't depend on it, and that's why it can be said it's a so-called cyclic coordinate. There is Rouse reduction theory and so on how you can get rid of it. And finally, you are left with a single second order scalar ODE for the angle phi, okay? And if you linearize it, you get this very simple system where this coefficient here is negative, referring that we are around the phi equals to 0, the unstable position. And this is the control force which we try to apply. So now clearly, if there is no control, then the phi equals to 0 is unstable. We have a negative stiffness here, or in the Rouse-Harris criterion, we have a negative coefficient in the characteristic polynomial. If we switch the PD controller on, then of course already we can make positive damping and positive stiffness term here, and the condition is that the differential gain D should be positive and the proportional gain must be larger than the weight of the beam, since the unit of the proportional gain is Newton also, since phi is measured in a radian. Okay, so this is why it looks simple and manageable. However, we have a reaction delay, which is denoted by tau, and this way the control force Q will depend on the delayed values of the angle and angular velocity in this controller. Now, we introduce these new dimensionless parameters, dimensionless gain, P and D. These are small letters referring to that. And omega n square, or omega n, is the natural angular frequency of the system when the pendulum is hanging downwards. Okay, so if it were oscillating at this around the stable position, then this would be omega n squared. Okay, so then the differential equation is here, and here is the characteristic function, which is a quasi-polynomial. That's a polynomial part with a negative coefficient here, referring to the instability, and these are the delayed term with this e to the power of minus lambda t. Lambda is a characteristic exponent. There are infinitely many, and they all must have negative real part in order to have stability. Now, if you do the D subdivision method, you just select the real and imaginary part at the critical values, you get a stability chart like this in the plane of the proportional gain and the differential gain. There is a stability boundary which refers to a saddle node bifurcation, or we engineers say that's a static loss of stability when one real zero crosses the imaginary axis. And the other curve here is a possibility for Hopf bifurcations, where self-excited vibrations may arise with this frequency omega. And if you calculate all these critical points of this diagram, you can even calculate that what are the typical vibration frequencies if you lose stability here. It will be just between 0 and 1/4 times tau. Tau is the typical reaction delay. In case of human operators, it's around 0.2, 0.3 seconds. So then it means that when we start oscillating in all these experiments, it is usually between 0 or half and 1 hertz. So we oscillate about 1 in 1 second, which anybody can check it if you play with the stick, or if you check yourself as you start standing. It can be seen that if you increase the time delay in the system, then this curve starts shifting to the left, and there is a critical point here when actually this curve goes like this. So actually all the stable regions disappear, and this critical time delay can again be calculated in closed form. It will be just t over pi times square root 2. Okay, these two beautifully rational numbers. These should be used to divide the time period of oscillation of the pendulum at the downward position. Okay, so this gives a time constant, and with this time constant we can express easily this critical delay. Numerically it's about 0.225. Okay, later I will refer back to this number, 0.225. Okay, so our reaction time must be faster than this. So for example, if we have a shorter pendulum, then it's more difficult to balance it, because then they oscillate with smaller time period of oscillation. Or for example, if this guy, for example, tries to balance himself, then it's nice to see that he extends his arms to the right and left. And one reason why he can do this, that if you hang it downwards and you measure the time period of oscillation, this way his mass moment of inertia is larger, and the time t will be larger, and actually it's already easier to balance yourself if you try to increase this time t by increasing your mass moment of inertia. And if you get sleepy, then your time delay starts increasing, and you start doing larger and larger oscillations. In the end, it really becomes unstable. Or you can also conclude that how the balancing organ, the labyrinth, works in human beings. You know, this is our inner ear, and it has these semicircular canals, and this semicircular canal, the viscous liquid starts moving and irritates this hair in these ampullas. And so this will give a good measurement of the velocity, and in this way the angular velocity of our head in all the three directions. It also has a part which is called static receptor, but it's very rough. It's our eyes are very good to check the angle and inclination. So eye is good for the signal which is used for a proportional gain, and this organ works very well with the differential gain. And we need both if we want to balance ourselves, as it can be seen here. And of course, if these two are messed up and they send inconsistent signals like after some rotations, you know, then of course you start losing your stability again if they are not. Okay, so that was more or less the introduction how the human beings do. And let's see now what the robots do when they try to repeat the same task. So practically, they work, of course, much faster. Their reaction time could be shorter, but it still exists a certain time. And this is a kind of sampling. So the digital control discretizes also the time. So from this point on, the control force is not varying continuously, but in like a step function. Okay, it can be represented this way, that if it is the signal and these are the time instance, tj, the sampling instance, tj minus 1, tj plus 1, the time delay is, or the sampling delay is tau. Then if you measure a signal, you need some time while you process it, and then you send it out, and there is so-called zero order hold, while this control force will be kept constant. Okay, so then here we go with our mathematical model. This is the inverted pendulum here. Uj denotes now the piecewise constant control effort or action in the interval tj plus 1. And this is a PD controller, but it is decided on the previous value at tj minus tau, what was the angle and the angular velocity with a PD controller. Of course, it is, again, the simplest possible case for a digital control setup. I use again the same omega n and time period of oscillation as before. And it's interesting to see that later it will become important that actually this sampling time with this piecewise constant can also be viewed as a time periodic time delay in the system. So practically we get absolutely the same controller, same situation if this time delay is imagined that it changes periodically this way as it's presented here between tau and 2 tau, which will practically mean that the average delay in case of these sampled systems will be, the mean delay is about 1.5 times the sampling time in this case. Good. So then since we have a piecewise constant right-hand side, we can introduce this three-dimensional state vector, the position, velocity, and the control effort. We can build up a three-dimensional discrete mapping. This would correspond to the Z transformation of the system. In the transformation matrix, you can recognize the hyperbolic functions, cosine hyperbolic, sine hyperbolic, referring to the homogeneous solution of the part. These are at the end, these are for the piecewise constant part which come into the picture. In the last row you see the PD controller showing up. Okay, and now we have to check oh yes, there is a new parameter here, omega, which is omega n times tau. The natural is dimensionless, and actually it is the same as the ratio of the natural frequency of the pendulum when it's hanging downwards and the sampling frequency, or the time delay relative to this time period of oscillation as you want. Okay, so it's an important parameter. Later there will be similar parameters like this, and we have to check whether all the eigenvalues of this three-dimensional matrix are within the open unit disk. This is the third-degree characteristic polynomial for the characteristic multiplier mu to the power 3, mu squared, and so on. 3 parameters only, PD and omega. And in the PD plane, you can construct a very similar stability chart as in the case of the analog delay control with a static saddle node stability loss and the Hopf. And if you try to determine that at what sampling time will this stable region disappear, then oh, I mentioned it here also, the Poya-Segre theorem. I learned it from both Sada and Niculescu in their papers. It's a very nice method. Before that, I always did it a much more complicated way. But if you because there must be a triple zero at +1 for this polynomial with 3 parameters. After second derivative, we can determine immediately this critical value of omega, from which we can calculate the critical value of the time delay, which is numerically 0.153 times this time period of oscillation that I mentioned. And that was 0.225 in the case of analog continuous control, which corresponds exactly to the fact that the mean time delay in the case of sampling is about 1.5 larger than the time delay in the continuous case. Good. So after this, for example, when we had projects with ABB and so on, we could play with it and we could balance a stick. Although originally surprising, but these robots, when they have only position control, the sampling time and the reaction delay is quite large, actually. It's very surprising. So when you have to do force control or balancing, they are not as good. Anyway, in this case, we can measure the angle and the angular velocity, and we can feed it back to the robot. It is much more difficult in the case of a Segway, because in case of a Segway, it's difficult to measure the vertical direction, where it is exactly. And so there are several tricks, of course, with gyros and accelerometers and so on, and integrating and screening and other things and filtering to get information about angle and angular velocity and to do this stuff. So that makes these controllers sometimes pretty intuitive and complicated and things like that. But I had an ingenious laboratory engineer. We name him Richie. That's why it's Richie's solution. And a Friday afternoon like this today, he just came to me and said that, well, why do we need this very complicated controller? I can do this whole thing with a single accelerometer that I put onto the Segway. And he explained me what he thinks about that. He said that, okay, well, let's place an accelerometer here on the inverted pendulum, what you could see on the photo before. This accelerometer is practically like a very stiff spring with a very small mass, you can think about a piezo or something. But practically it measures this very tiny distance or elongation of this, and this is definitely proportional to the angle phi, because the corresponding component of the gravitational force will be m0 g sine phi, m0 being the mass of this little thing, okay, with this huge stiffness there. And then, since he has this angle phi, he has the PD controller, and he will apply the torque here between the wheel and the pendulum. And after multiplying this P0, D0 with these numbers, definitely he will get something which should work with this differential equation. Of course, I told him that no, it will not be as simple as that, because the pendulum itself, or the body of this pendulum, will also accelerate. So there will be an angular acceleration here. Also, there will be x double dot, but let's concentrate on the angular acceleration, phi double dot only. And if you put it into a PD controller, phi triple dot will also appear in the equation. But if there is a phi triple dot, that will already mean that there's a jerk already. It's the derivative of the acceleration. And if you have any tiny delay in the system, as you will have, even if you have the very fast processor, you will get a so-called advanced differential equation. So a higher derivative will be delayed, which will mean that you can rearrange in a way that the highest derivative depends on the future. So even philosophically, it's a bit strange. So, and it is proven that all these advanced equations are unstable. They have infinitely many characteristic roots on the right-hand side, so it is hopeless. It will be absolutely unstable. And that's very uncomfortable when next Monday morning, the guy comes in and puts it onto my desk, and it starts working perfectly. And so then you just don't know what to say. So you are here with this huge theory, and you think you know everything about delay systems, and then he just goes home and does it, and it seems to contradict totally to this problem with the delayed jerk in it. So then I start thinking about it, and with Thomas Hinsberger, we start thinking about it, what the hell may be going on here? And clearly, the only difference with the theory is that, of course, the robot works in a digital way with sampling and not with continuous time delay, as the theory considered it with the advanced equation. So here is again with this discrete delay, and now it is described with the same periodic time delay as I showed it to you. And okay, so we start thinking, well, maybe with this one it works, even if he uses the jerk. But if we try to make it more and more fine, we could approach the continuous time delay here. So in some sense, we must have some continuous connection between these advanced equations and these sampled jerk feedback or something like this. So we consider this equation where this time delay tau was varied this way, and we wanted to see how we can approach with this one, that one above. Okay, so this one is the sampled, and that one is the continuous or analog delay, and that's where the sensitivity for parameters comes into the picture. So I will try to explain it here now with the simplest possible examples. That's the first order. So not with that example that we did with the pendulum, but did this first order retarded DDE, because only the axis feedback like this. This is the characteristic function. Already in 1951, the stability of this problem was solved by, it's called Hayes equation. And this is the digital version of it, when instead of the continuous delay, we have this kind of sampling, where this R times H, or the tau, is considered to be 1. And we try to approach this system in a way that as we, this R will be the approximation number, say, it will be larger and larger, and H will be smaller and smaller. And so the time is discretized this way because Tj will be J times H. Okay, so I will show a figure about it soon, you will see it. And then this one can be solved again the very same way as I showed you in the previous case. There was only a 3-dimensional vector. It will be R plus 1-dimensional. In this case, this will be the coefficient matrix here in the discrete matrix. This e to the power of AH, this is from the solution of the homogeneous part. This part comes from the piecewise constant non-homogeneity, inhomogeneity in the system. And in the rest, there will be, like in the Cauchy transformation, these ones. And the size of the matrix will be proportional to this R, how fine is the resolution. So the higher the resolution is, it will be the stronger. Okay, here you can see it. So in this case, the digital case, when R is equal to 1, this is the one. And this is how we approach the Hayes equation. And now let's see the stability charge. This is the one we know from the literature, saddle node and Hopf-line, stable, unstable. And here for H equals to 1 or I equals to 1, the stable region will be somewhat smaller, which is reasonable because the average delay is larger. And actually, as we start approaching the continuous case, we will approach perfectly, we will converge to this stable region. So everything is according to our expectations. No problem. In the neutral delay differential equation case, when the derivative is delayed, for example, I saw it first time in the book of Komanovsky-Nosov to solve this problem, although it doesn't seem to be, so actually it's simpler than the original Hayes equation, but still. In the digital case, if you repeat the same procedure, you build up the coefficient matrix. Now the derivatives will be here. Oh, someone left the microphone on. Anyway, yeah. In the second line, you will have the velocity showing up. And if you look at the stability chart, this is the exact stability chart. It's very simple. A must be negative and B must be between +1 and -1. Okay, this is the exponential stable region. This one outside is unstable. And if we have a look at it here, when we have the worst approximation with this one, when the delay which is 1.5 times larger than the continuous case, we get a much larger stable region. So the neutral equation actually, the sampling helps. It behaves better than in the continuous delayed feedback. And as we increase the approximation, finally we start converging to this. So finally we can agree, okay, fine, finally there is no problem with discontinuity. Now let's see what happens with the advanced case when we have a higher derivative delayed, which leads to this characteristic polynomial, or we can transform the equation for the second order form when the future will determine the present. So even philosophically, it's, but anyway, from mathematical viewpoint, it is possible, and it's the very same characteristic function, but Asgos already proved it in 1964 that in these cases, infinitely many characteristic roots are the right-hand side. It's absolutely unstable. Let's see what does the digital situation. We build up again the matrix. Now the accelerations will be in the state vector, a similar coefficient matrix. Here are the approximations, and here are the stability charts. Here we have this strange situation that it's infinite with infinitely many unstable poles. We have all here, except when b is equal to 0 and a is negative. Okay, if this term is not here and a is negative, then you have exponential stability there. On the right hand side, what happens that with this system we get a huge exponentially stable region here. And as we start approaching this one, it will not converge to this line, which was a surprise. Of course, for a long time we thought that there must be some problem with our approximations, but no, this is the case. Here we can see that although the number of unstable roots increases here, this region remains exponentially stable. Or in another view, if h is put on one axis and this is b, this is 1 over a, then when h is equal to 0, then we have infinitely many unstable poles. Here we have a continuous change to that above this curve because the number of unstable poles is proportional to 1 over h. Down here, we have exponential stability, and suddenly we have infinitely many unstable poles on the right hand, kind of suddenly. So this is the region where finally Ritchie's segue worked with an acceleration and jerk controller, which was a kind of surprise. Yep. Now, let's see another example, which in some sense will be similar, also shows this extreme sensitivity for the delay parameter. And this is about this electroacoustic system. Sorry about this sound, just for representation, what I'm speaking about. Okay, it happens on very different frequencies in public address systems, and it's very annoying. And even the frequency of the vibration is jumping up and down. So if you try to model it, again, it's a very primitive, oversimplified model, but it will show some of these physical phenomena. We consider that here's a loudspeaker, the air is considered just as a beam, and here is the microphone, and it is fed back through a amplifier, proportional gain, and there is a delay in the electric circuit. Okay, so we will kind of measure the pressure or the force here, and we will give a force on the other end of it. It will be a PD, so a distributed parameter system. U will be the longitudinal deformation. These are the parameters: density, elasticity, cross-section area, and length of the beam. And this is the wave equation, okay, where c is the speed of sound. So it will be a PD, a partial differential equation, which needs two boundary conditions. On the right side, we have a built-in rigid end, so the position, the displacement is 0 there. On the left side and the right side, we connected with this delayed feedback, namely that the force which is measured here, amplified by k, will be the same as it's applied on the other side. And since this force is proportional to the strain through the modulus of elasticity, it will be referring to u prime, okay, the strain. And this delayed value will appear in the boundary. So of course, Miroslav Krstić has these many papers and series of publications as boundary controls for PDEs. But it seemed to be pretty frightening first at what we can do with this. So first we tried some finite degree of freedom approximations. Well, it's a very primitive, even not a finite element method, just finite discretization for the space coordinate, with which you get a diagonal mass matrix here and a stiffness matrix, which is 3 diagonal with a belt here, which from the modulus of elasticity, you can get the stiffness K, and the feedback with the proportional gain, capital K, will be here in the upper right corner, which connects the two ends of this system. I will use omega-1 as a parameter of this is the first longitudinal natural frequency of the system. And I will use capital T, which here will mean the traveling time of the traveling wave, how much time it needs to travel along the beam, L over C. And the first natural frequency can be also expressed with this. Now, if you consider the 1 degree of freedom approximation, you will get this delayed oscillator. I think for many of you, it's very well known how it looks like, how the characteristic function, real imaginary part, D curves, and the plane of these two parameters. One is the time delay in the electric circuit divided by the time needed for the traveling wave to go along the beam. On the other axis, there is the proportional gain K. Okay, you will get these D curves. The formula in closed form is there. And these will be the asymptotically stable regions within it. Okay, then you repeat it with 2 degrees of freedom. You also get the D curves. It starts a bit more, getting more complicated. And the stable regions starts getting a bit more fragmented. If you compare it with the original 1 degree of freedom boundaries, you see that practically within those boundaries, we just lose stable areas. And if we go for the 3 degree of freedom, we lose even more stable areas. And if we go further up, it turns out that at 9 degrees of freedom, or at least to the best of our calculations, we couldn't get any unstable region at all. So we had the conclusion that although mathematically we couldn't prove it, but definitely numerically it shows that n larger than 8, no exponentially stable domains left in this chaotic set of D curves. So it gives the impression that probably the continuum case is unstable. But let's check this PDE with the help of the D'Alembert solution and with this delayed feedback. So we have a traveling wave solution here with this function f and g. With this boundary condition, first we get that g is just the delayed value of f when the time delay is 2t, so as it runs to and fro the traveling wave. And then if we substitute this back to the second boundary condition, we get a kind of neutral delay differential equation with 2 time delays in it. One is 2t, and the other one is t plus tau. So one delay is while traveling waves in the mechanical part goes up and down. Another time delay is when the mechanical wave and then the electric wave runs around. Okay, and if you check the characteristic function of this, you will get something like that. And the so-called essential part of this neutral delay differential equation is just a difference equation, this one, if you get rid of these derivatives, with the 2 delays I just mentioned. So the question is that whether this function is, this iteration, or I don't know how to, a difference equation is stable or not. And once I had a discussion, it's in the early 2000s or something, with Werner Lünel at a conference, and I posed this question to him. I already mentioned it in my book also, that I didn't know how to solve this problem when you have 2 delays. For example, they are irrational relative to each other. Then what is the condition for A1 and A2 have stability? And a few years later, with Hale, Lünel came out with a very powerful theorem where they proved that if in a difference equation like this, the delays are rationally independent, so their ratios are always irrational numbers, and you can have as many as you want, then the necessary and sufficient condition of exponential stability is that the sum of the absolute value of the coefficients is less than 1. So it practically means in our case that in this equation that we obtain this public address system, we have the sum of the coefficients is larger than 1, or actually it can be 1 only if we have no control, which doesn't have a sense. So it looks that our system is unstable for any irrational ratios tau over t for any gain k, which actually was also suggested by the numerical approximations we started doing by the finite difference approximations. But still there is a tiny hole in the theory that maybe mathematically it would be interesting to see whether there's, but whether physical any sense to investigate this problem further. But then there was this nice example I found first in the book of Michaelis and Niculescu, where they presented this very simple difference equation where the ratio was rational, 1 to 2, but the sum of the coefficients was larger than 1. And actually they could prove that they could calculate in closed form all the characteristic roots, and this system is exponentially stable, actually. They even showed that for the slightest perturbation it becomes unstable, and they could prove that there is no, so the example there is about continuity of the spectrum, which doesn't fulfill in case of the delay parameter, and there is a lot of theory behind it regarding operators, and in infinite dimensional systems it can happen. So anyway, just for mathematical curiosity, let's check where are these values, okay? Where are these rational values? Whether in our case we can have it, and we can. The tau over t will be p over q. So in this kind, with two integers, we can express the ratio of these ones, and h can be a common basis, and we can introduce a characteristic multiplier with e to the power of h lambda, and we should check now whether all these are less than 1 in absolute value, and the characteristic function for the characteristic multipliers will be transformed into this polynomial, mu to the power p plus q and mu to the power p minus q minus 2k. Well, so it's already a polynomial, and but it looks first hopeless, and it was really with jungly with a lot of calculations actually for several years, just checking all the possibilities which can happen, and it turned out that there are cases when it can happen that these roots are inside the unit circle. A situation like this, when most of the roots are there, but there are some which come in and then they just go out again, but there for a certain time they are indeed inside the open unit disk. And that leads us to the sensitivity to the delay ratio. Here we could calculate in closed form what is the parameter combinations where we have exponential stability. And in the delay ratio and the control gain plane, we have these black lines where we have actually exponential stability. Exponential stability, while just for the tiniest perturbation, we already have instability. On the top of that, instability with infinitely many roots. These tiny regions are just in the middle of those which we obtained with the 1 degree of freedom approximation. If you add damping to the system, it turns out that still it was worth doing this calculation, because around these tiny regions, for internal damping, even in closed form, we could express these stability boundaries. As we increase damping, there are larger and larger exponentially stable regions, but these boundaries are actually fractal-like, and it cannot be seen well. And these and we couldn't zoom in. It's a lot of calculation to do these, but at least the vibration frequencies show that it's extremely rich around these regions. What kind of vibrations and with what frequencies they can occur. So actually it's a fractal-like surface, even in the presence of damping where we are away from this problem. Okay, so now we just have a few minutes to go back to consequences which really affected us in some calculations and in the ERC project with machine tool vibrations. As an introductory example, we tried to investigate these hardware-in-the-loop experiments in the case of different oscillators, like the stick slip model. I hope you know this well. When you have this Tribeck friction force characteristics, and this is the belt of the speed of the belt. V is the bifurcation parameter, and in these systems you get a bifurcation diagonal like this. This is the speed of the belt. For low speed, you have an unstable equilibrium, it starts oscillating. For higher speeds, the system becomes stable, but there is a subcritical Hopf bifurcation here. The reason why we selected this example for a so-called hardware in the loop experiment, because A similar situation occurs in machine tool vibrations, just in a much more complicated setup. Actually, in this case, we could check, for example, experimentally that indeed, for example, in this speed, when you have a disc, you have a tiny brake pad put there with a soft spring. If you perturb it, it starts oscillating with this vibration amplitude. But when I push it back inside an unstable limit cycle at a subcritical bifurcation, then it settles at this stable point. Can you see now? I push it back and now it settles. And then if I hit it again, then it starts vibrating again. So this is that we wanted to produce in a hardware-in-the-loop experiment, which means that we keep a part of the real physical structure, which in this case was only a 1 degree of freedom oscillator, and the friction force is emulated or produced by a control loop. This is here with an actuator that would emulate the friction force. This we measure the position of this. Here is the controller, and the controller will produce the friction force with a sampling and delay, okay, as it is mentioned here. So we wanted to see what's the effect of this sampling and delay on the system, whether we can still identify the same dynamic behavior as it should be. And so on this diagram, here is the belt speed, 0 and V. It is unstable, stable. This is the critical point, the Hopf bifurcation when it happens. And on this axis, you can see the ratio of the natural frequency and the sampling frequency. So when we are infinitely fast with sampling, then we are here at 0, and then we are in the physical case. And then when the sampling frequency is finite and we start shifting to the right, it turns out that when it is, for example, when the sampling frequency is only 6 times higher than the natural frequency of this loop, then already everything will happen just in the opposite way as it should be in the real experiment. And if we add the damping, it was an undamped case calculation in closed form, and it was also measured, checked with measurements. Here is the nice subcritical bifurcation that we could identify when the test was running with 500 Hertz, but when we ran it with 67 Hertz only, then everything was stable. So from engineering viewpoint, it's even worse. So if we are not careful enough with checking these sampling frequencies, then we can get qualitatively wrong result and a dangerous result, because the system, the hardware-in-the-loop system, which now they use it in development of brakes and so on, it very often shows stability because this sample delay stabilizes the system more than it should be. Okay, but if we go down to the 2 millisecond sampling time, which refers to the 500 Hertz sampling frequency, then we could get the same stable oscillation here. Now it's slow motion just to see that it really oscillates, and then we catch it and then it gets back to the stable equilibrium. Okay, and if we perturb it again, we push it outside the unstable limit cycle, then it starts vibrating again. Okay, so how did all affecting vibrations? So here you can hear again this uncomfortable sound, which is not the sound is the major problem, but the quality of the machine surface and the steps of the modeling. I will not explain all the steps of the modeling and how we get that the cutting force will depend on past positions of the tool. It's a so-called regenerative vibration. But practically, the equation of motion will be a delayed oscillator. Okay, on the top of that, it's a slightly damped oscillator because machine tools have very slight damping, while they are very stiff, so the natural frequency is very large. So it's really close to an almost undamped system. The nonlinearity is similar to the Strebach force and asymmetric nonlinearity. And on the right-hand side, we have also already a delay term, which is proportional to the rotation of the rotational speed, inversely proportional to the rotational speed of the workpiece or the tool. Okay. So now, if we wanted to do this hardware-in-the-loop experiment, we wanted to do semi-virtual milling. So the machine tool was here, but we wanted to emulate the real cutting process. We had to measure displacement and to produce the cutting force with electromagnetic actuators. And during the design, we already had good estimations for the required sensor accuracy, for the required force magnitudes by the electromagnetic actuators. But it was a critical point that what kind of real-time computation device we need and how we have to be prepared in order to produce all the dynamic phenomena which appear in the real environment with this hardware in the loop. And now we have the sampling delay of the hardware in the loop system, plus the system itself has a large time delay in it. On the top of that, if we have milling, then the situation is even worse, because then there is a time periodicity in the coefficients. So that was the calculation of Thomas Moner when if we have the original stability chart of milling in a pretty complicated case, this is when the analogous model with a single time delay in it and the time periodicity in the coefficients shows that these are the unstable regions, these are the exponential stable regions, we call it lobes, instability lobes there. And there are different kinds of vibrations which occur here, sometimes period doubling, sometimes Hopf bifurcations or Nymark-Zucker as you want. The spindle speed from 3000 RPM to 30,000 RPM refers to about 1 to 10 millisecond time delays in the physical system in case of two cutting edges. This is the natural frequency, pretty high in case of this machine tool. Or the spindle. And if we start doing the hill, and this delta t refers in microseconds to the time delay of the sampling, we can see that we get something crazy. So very quickly, this otherwise pretty complicated stability charts actually goes in the wrong direction. So it shows too much stability, and also extremely sensitive for this delay tau, depending on how it is combined with the other delay. Of course, these are mainly numerical results only, but it already showed us and helped us to estimate this requirement, the 100 kilohertz sampling frequency, to provide 200 samples per rotation. And it also gave us guidance how we have to organize the parallel calculation in the system, how much we have to jam all this into the fastest possible FPGA modules that was available at that time at the market, which was also pretty expensive. And only this way we finally managed to achieve that the whole system started running. And now you can hear as we speed up the spindle, so we change the time delay system, then the system really produced at certain domains in these instability lobes, these vibrations. You will also hear at the end as the sound of the spindle goes up. And unstable regions are wider and wider. So this is, for example, a stability chart which is measured semi-empirically. Okay, here are these lobes, and everything seems to be okay at the moment, although we still have a lot of things to do. But I just wanted to show you one example how all these break down finally for kind of practical applications. So as a conclusion, I mentioned only three: some rationally dependent delays in neutral or sampled advanced systems, so you can even try to feedback the jerk, may result in exponential stability, while all rationally independent delays leads to instability. This is not just mathematical curiosity, but it may be relevant physically. Models of OD feedback, deep drilling, hydro in the loop present extreme sensitivity of stability and system parameters, which is confirmed by practice. The occurring vibration frequencies are kind of unpredictable sometimes, or at least surprising. The closed form analytical results for the necessary and sufficient conditions of exponential stability in robustly unstable neutral delay systems provide challenge for advanced numerical software, with which I wanted to say that the finite element analysis in these cases may not converge, even if we try to make the spatial resolution thinner and thinner. Definitely we know that it will not converge, so it will be very hard to make it convergent if it happens. Okay, that was all just the picture of those whom I had no time to mention by name. The group on the human balancing research group, also mentioning our Chinese and American colleagues whom we had this cooperation, and the group who took part in the machine tool vibration project, the different working groups.